So we're going to go ahead and introduce another name for the instantaneous rate of change, or slope of tangent, slope of curve, that you've had some practice working with now uh, within the limits unit. But we're going to add another name to those. And so instantaneous rate of change, slope of tangent, slope of curve, can also be called a derivative. And this is a big chunk of what calculus works with, are derivatives, because they tell us instantaneous rate of change, slope of tangent, slope of curve. So, kind of our formal definition, the slope of a tangent as you work through with the limits is we're finding the slope between a point of tangency at a, f of a, and a point just a little bit to the left or right of it at a plus h, f of a plus h. And you find the slope between them gives you this piece, and then the limit as h approaches 0, that, remember, h is the horizontal distance between the points, moves the points closer together until they're infinitely close. Well, derivative more is the same idea, we just don't know what the point of tangency is. So both of these are doing the same thing. A is a value we know, x is the variable x, which we don't know, but both of these are called a difference quotient. And these are important to know in calculus because we do use difference quotients quite a bit. And even when we learn some shortcuts to make the difference quotients go faster, it's still a concept you need to know. If using a point of tangency, a point a little bit away, and do a limit to move them closer till they're infinitely close. Some vocabulary that you'll hear me using through these videos. If a derivative exists at a point, then we say that f of x is differentiable at that point. So differentiable means the derivative exists. If the derivative exists for the entire domain of a function, then we have a differentiable function. In terms of notation, it can be a little bit confusing. There's a lot of different notation, mainly because Newton had his notation and Leibniz had a different notation, but for the same concepts. So the first notation, which is Newton's, is called prime notation, in which we use prime marks, which are really superscript Roman numerals, but when we see them, we say prime. So we could say f prime, or we could say y prime, depending on how we define the function. These are very nice. They're very brief. Drawback is they don't tell us what our independent variable is, especially if we have multiple independent variables. That can be very confusing. Leibniz notation, a little bit longer, however, is very nice because it does specify and emphasizes what we're doing a derivative with respect to. In other words, what our independent variable is. So it's written as a fraction. However, we never say over. We would just say dy dx, or df dx, or d dx of f of x. And so these are all just different notations that you may want to look over to make sure that you're okay with these. So for example, if I wanted to find the derivative, or f prime of x, for x cubed, if you notice, we're not given a point of tangency, so we use an unknown point, which would be at x cubed. And then I would need a second point that I would do by adding h to the x, which would then be at x plus h quantity cubed for the y coordinate. So then I want to move the 2 points closer together, finding the slope between those 2 points, change in y's, and then the change in x is just h. Well, if I multiply out and do my binomial expansion on x plus h quantity cubed, that's going to be x cubed plus 3x squared h plus 3x the first h squared plus h cubed, then minus the x cubed all over h. Well, I'll see my x cubes cancel, and I can divide every term left by the h that's in my denominator, So I'm doing the limit as h approaches 0 from both sides. Notice it is a two-sided limit of 3x squared h plus 3xh plus h squared. And I can now do substitution. Note that the limit is saying h is the variable, so I'm only substituting 0 for h, not the x. Oh, made a mistake there that hopefully you caught. That should only be 3x squared. The h is canceled. My apologies. But when I do my substitution, I just get 3x squared. And what this tells me is that this is the slope of the curve at some point x cubed. And this is something we do a lot in that, let's say I wanted to find a lot of different slopes at different values on the x cubed curve. Well, rather than going through all of this work every single time, it's a lot easier if we do it once with a generic point like this, so that we can then just plug in different x values. So say I wanted to know the slope of the curve when x is -1. Well, I just plug -1 into my derivative here, I get 3. Or what's the slope of the curve when x is 2? Well, I plug 2 into my derivative, I get 12. And so it allows us to find multiple slopes very, very quickly.